So, MapReduce programming paradigm. This is quite simple. In writing and working with data on HDFS, everything that you do is broken into a map and reduce processes. On map, you operate on all data elements of the collection by applying the same operation to each individual elements of this collection. So you can see where the mapping comes from. As you have a huge data set broken into many blocks, what the map process is it is going to run the same operation on each block and process each data block. And as the blocks are distributed across a massive compute network, when you write a map procedure, you effectively already develop a parallelizable version of the mapping process. So go ahead and run this example code to demonstrate the map. Let's say you have an array of input data going from 0 to 4. You want to define a square function as return x, correct? So Python has a function called map that allows you to map this square function to this data set, input data set, and we can look at the output of that. So within a map function, you can also make it becoming a lot more complicated so that you can embed that multiple operations within a map function. So let's say I want to do the square, but I also want to do the filter only for those that is larger than 4. So I just embedded that algorithm within my mapping function, and I run the map again. So the first 3 doesn't return anything, and the last 2 is where I actually have the values. If you cannot keep up with it, don't worry. So all of this is available on the website, so you can go back and run that later. So same thing. So let's say I have an input data, and I want to break it down to smaller pieces. Then again, map can help you to do that. So mapping functions apply the same operation to all the elements within the list, and it will return something out of that. And then the reduce function is an operation that takes those intermediate output value and aggregate that into a final result. So let's say if I have a reduce. So remember that this is my map output 1, which is a list going from 0, 1, 4 to 16. My reduce functions, so I'm taking the reduce function from Python as an example, can apply the reduce function to that collection of data and give me the final answer. So with that, let's do a quick exercise to write a MapReduce procedure. Let's say I have the following data set, write a map function, write a combination of map and reduce function to find the largest square value within this array. So within the context of Hadoop MapReduce, as you have data being chopped into blocks, as I said before, a map function can be thought out as being applied onto each individual block. And naturally, the design of HDFS allowed you to, so recall that the map and reduce function that we had in the examples above. If I have that array of 10 elements, or if I have the same array of 10 million elements, I can still reuse the same map and the same reduce function to do the calculation that I want. So because of the infrastructure of HDFS underneath, MapReduce is naturally parallelizable and naturally highly scalable. If you want to make MapReduce run faster, you only have, when you have larger data, if you can have more computer and you can spread the data blocks out across more computer, then your program will run faster. Of course, there will be an added cost of overheads. There will be a point of diminishing return when investing in more computer is not worth it. But basically, MapReduce allowed companies to be able to scale out their resources easily without having to worry about changing the algorithm of the analysis. So, some of this information on the map and reduce as we have it on HDFS. So in this example, we are doing everything within the context of a single computer. The map and reduce you are running out of the parameter node that you allocated. But within HDFS, when the map operation completed, the intermediate data is going to be stored locally. So the reduce will need to reach out, and so the reduce will need to get this data. And if you want to have the reduce to be parallelized also, it will need to have a mechanism to distribute the intermediate data among the reducer. So, but again, this is for you to be aware that these are the operations that needs to be done, and also for you to know that all of this are by default already managed by Hadoop MapReduce, and you don't have to worry about that. You could attempt to try to modify the default distribution framework that they have. Hadoop MapReduce has a lot of configuration options that you can set to optimize your MapReduce program, but by default, the programmer does not have to worry about this. One important thing is within Hadoop MapReduce, when we talk about one element of data, it is not a single piece of data. An element of data always comes as a pair, key and value. The key represents the identity of the data. It could be, and then the value is the value of that data. The key here doesn't really mean the identity of that specific data block, but it's more like the identity of the groups of data that belong to the same type, and the value are the various value of each of those elements. So we'll see how the key value pair help with the Hadoop MapReduce process later on. Some other thing, Hadoop MapReduce will shuffle the map output data across computers, and in this shuffling process, it will automatically sort all of the intermediate data according to the key. And it will also partition the placement of this group of intermediate data just so that minimal data transfer is needed. So again, when talking about Hadoop MapReduce, we are talking about massive amount of data, and we do not want to move data across the network. That is just a bad thing to do. We don't want to do that.